Okay, this is Nate again. Tempo Project 2, Problem 2. Let's go. So, steam enters the condenser of a steam power plant at 20 kilopascals and a quality of 95% with a mass flow rate of 20,000 kilograms per hour. It is to be cooled by water from a nearby river by circulating the water through the tubes within the condenser. To prevent thermal pollution, the river water is not allowed to experience a temperature rise above 10 degrees C. If the steam is to leave the condenser as saturated liquid at 20 kilopascals, determine the mass flow rate of the cooling water required. Alright, so for this problem, energy in minus energy out equals delta E of the system. First assumption that we'll make is that it's a steady system, because it doesn't say otherwise, so there's not going to be a change. So E in is going to equal E out. So now we're going to write our big dog formula up here. Q in plus W in plus the sum of mass flow rate times H plus V squared over 2 plus GZ equals Q out plus W out plus the sum of the M dot H plus V squared plus GZ. Sorry, ran out of room there. This is all out. Okay, so another assumption that we're going to make is that it's there's no heat loss in or out of the system apart from where the water and the steam are circulating and changing, so we can get rid of that. There's also going to assume that there's not any work being done because there's no pistons or any parts moving inside or shafts or turbines or anything like that. Also, it's a stationary system, so we can get rid of kinetic and potential energy. So we're left with the sum of the M dots in equals sum of the M dots out. We can kind of divide this into two separate mini systems. The first is what I'm going to call the tank. For that, we're given M dot 3. We're going to call this M dot 4. And then the water coming in, we'll call M dot 1. And the water going out, we'll call M dot 2. Alright, so if we look at everything here, continuing on with our equation, we're going to have M dot 3 H3 plus M dot 1 H1, those two up here and here coming in, is equal to M dot 4 H4 plus M dot 2 H2. Okay, going back to our kind of two separate systems, we can see, the water flowing into the tube and out of the tube. So we know that M dot 1 equals M dot 2, which from here on out I'm going to substitute those in for M dot H2O. Okay. We also know that M dot 3 is equal to M dot 4, which I'm going to call M dot tank. So now, doing a little bit of algebraic manipulation, we can substitute using these more or less three equations, and we're left with M dot H2O is equal to M dot tank times H3 minus H4 all over H1, or H2, excuse me, minus H1. Alright, so we're going to go to the next slide now. So I'm going to rewrite that here on this slide real quick. So m dot H2O equals m dot tank H3 minus H4 all over H2 minus H1. So, what do we know? We know m dot tank, that was given to us in the problem. Now, H3 and H4, let's see if we can find those. For the water flowing into the tank, they're giving us a pressure of 20 kPa and a quality of 0.95. So, using those, we should be able to find H3. So, H3 is going to equal HF plus X times HFG. Using our tables, we get H3 to be we'll put in the numbers here first, actually. 251.42 plus 0.95 times 2357.5, I believe, if I can read my writing, for a value of H3 to be 2491.1 kilojoules per kilogram. And then H4 is also at a pressure of 20 kilopascals, and they're saying it's leaving as a saturated liquid. So we can go and look at our values on the table for HF at 20 kilopascals on table A5 and see that that is 251.42. Okay, so now we have H3 and H4. Now, what about H2 and H1? They don't give us a whole lot of information. They just say that water is coming in from a lake, which we can assume that lake is approximately at air temperature. They're not saying it's like frozen in the winter or in the middle of the desert. So, we're going to assume, 20-ish, 25 degrees Celsius. All they're saying is that it comes in at one temperature, that air temp, and then it can't get any more than 10 degrees warmer. So, for H2 and H1, we don't really have anything to go by to look up our H values on the tables. So, we're going to have to figure out another way. We know that H2 minus H1 can be treated as delta H, which we know that delta H is equal to Cp, the specific heat, times delta T, which is nice because we know delta T is equal to 10 degrees because that's the maximum amount that it can rise. So we know that. Now Cp, we're going to have to look at table A3 to find our specific heat of water, which they've got a couple different temperatures for that. We're going to go with the one at 25 degrees Celsius since that's going to be approximately air temperature. So our Cp value is equal to 4.18 kilojoules per kilogram Kelvin. So now we've got 4.18 times 10, which we can sub right back into that part. Now, magically, we've got all of our values. So we'll start putting in our numbers here. M dot H2O equals, I'm going to save the mass flow rate of the tank for the end. So we've got 2491.1 minus 251.42 all over 4.18 times 10. Now our mass flow rate of the tank, they gave it to us as 20,000 kilograms per hour. Now we might need to be careful there because we're going to want that in kilograms per second. So we'll just have to take that times 1 hour per 3,600 seconds. And we're getting a mass flow rate of H2O to be equal to 297.7 kilograms per second.